Welcome to the last lesson in the philosophy section of Logic, Language and Information. We're looking at vagueness and the Sorites paradox. We've got an argument which seems to be valid, which leads from premises which seem true to a conclusion that seems false, and these seemings can't all be right. In this lesson, we'll look at the way out that says that the premises aren't all true. This is one of the four options in response to the paradox that we've already seen. This is the third option, according to which logic does apply. The argument is valid, but it isn't sound. The premises aren't all true. We're exploring ways that we can reject the many-valued logic of Vagueness in favour of the Boolean two-valued logic we've been exploring in much of this subject. So let's go back to our strip of colours, shading from red to yellow, and think about what we might say about the different statements, this patch is red, when we're pointing at different parts of the strip. Now, if I divide the strip into 8 even patches, it seems to me, at least on my screen, that the first 2 patches are definitely red. And the last 4 are definitely not red. And the 2 in between are a judgment call. So in the first row of this table, I've put how things seem to me. Now, your eyes are different to mine, and the colour reproduction on your machine might be different to the one here, so it'd be reasonable for us to disagree on this. But I hope for everyone who can see the strip, some of it's clearly red, and some of it's clearly not red, and there's a fuzzy range in the middle. Now, the next 3 rows of the table are the two-valued ways of filling in this gap. We could say that nothing in the gap is red, that's the first row. Or we could say that patch 3 is red and patch 4 isn't, that's the next row. Or if we wanted to be generous, we could count patch 3 and patch 4 both as red. Now, there's another way, of course, of filling in 2 values, but this way is worse than the other 3. Can you see why? In this row, we've counted patch 4 as red and patch 3, which is more red, as not red. Not every way of assigning zeros and ones to the gaps are as good as any of the others. What we're looking for is ways of filling in these gaps so that everything that we take to be determinately true is true, and everything we take to be determinately false is false. Now, some of these facts are the red values that I've coloured in each row. These are the things that we started off with, where we said that the things on the left were red and the things on the right are not red. But another fact that we take to be determinately true is, for example, if R4, then R3. If this counts as red, then that counts as red. And that's true in the first 3 of these rows, but it's not in the last. So we're going to leave that one out. The other 3 rows, on the other hand, seem to be equally good ways of sharpening up the table that fit with what we take to be true. And one way to understand vagueness is that there are multiple places where you could draw a sharp line, and each is in some sense as good as the other. This is the core idea in all two-valued approaches to vagueness. And I'll be looking at 2 different ways that this core idea can be understood. The first approach is what's called supervaluations. According to this approach, the collection of all of the appropriate two-valued valuations, here, these 3 rows, together model the world. And we'll call a collection of two-valued valuations a supervaluation. It's a valuation of statements that allows for indecision. The world says R1 and R2 are true, the world says R5, R6, R7, R8 are false, and the world's kind of undecided about R3 and R4. Statements are either super true, like R1 and R2, these are statements which are true in all of the valuations. Super false, they're the statements which are false in all of them, or in the gap. There's true in some, but false in others. Now, this is not the same as 3-valued logic. Notice that R3 and R4 are both in the gap, but the statement R4 implies R3 is super true. That statement is true in each row. If R4 is true, R3 is true. While R3 implies R4 is itself in the gap, because R3 implies R4 is true in the first row and true in the last row, but false in the middle. So this is different to Vukajevic's picture about how to do truth-value gaps, because for Vukajevich, at least if R4 and R3 both had the value half, then R4 implies R3 and R3 implies R4 would have the same value, 1. Now we'll say that something is a tautology if it's super true in all of the supervaluations. The tautologies in this picture are exactly the same thing that are the tautologies in standard two-valued logic, because if something is true in every two-valued valuation, it's true in every valuation in a supervaluation too. Now, here's a question for you to try to see how you're going. We're back with our 3 circles. Now let's say that circle 1 is large but not red, circle 3 is red but not large, and that you could go either way with both redness and largeness for circle 2. That means we have 4 different valuations in our supervaluation. Which of the following statements count as super true on this picture? How did you go? If you've got questions or comments, or if you'd like to explore these issues further, take a look at the course notes for this section and head into the discussion boards to follow things up, and I'll keep looking to see how you're going. So let's see what supervaluations have to say about the Sorites paradox. It looks like we have a range of valuations, given that there's a range of patches in the strip that are equally good candidates for the cutoff point for being red. So, for example, everybody thinks that the first patch is red and the last patch isn't, but maybe R1 and R2 and R3 and R4 and Ri are all true, but Ri plus 1 is not true, and the bigger things aren't. That's one way. Or you could count more things as being red, and maybe J is the last red point in this way of cutting things off. You'll have a range of different valuations like this. Each valuation in the supervaluation will have a borderline somewhere, and each will make one of the premises, Ri implies Ri plus 1, false. But which premise is false is different in each case. The argument doesn't have each of its premises true, even though each premise is true in an overwhelmingly large number of cases. So that's what supervaluations say about the Sorites paradox. The premises aren't all true and can't all be true, but which premise counts as false is different in each case. And so that means lots of the premises are kind of in the gap. Now, look at the general statement, there is a spot which is red and the next one isn't. That statement is super true, or at least it would be if we had a way of stating it in a language, because the statement, there is a last red spot, is true in every valuation. And this leads us to a natural question. Is there a sharp cutoff point? Is there a point on the strip which is red and the next point along isn't? The idea was to say that there wasn't a precise cutoff point, but a range of cutoff points. But the statement, there is a precise cutoff point, seems to be true in every valuation. So by the lights of the supervaluationist, it should be super true. This is one of the reasons why not every person who wants to retain two-valued logic thinks that supervaluations are the way to do it. So let's go back to the two-valued picture we've already seen. We've got the idea of there being a range of two-valued valuations that are equally good. We're going to stick with that idea, but we're now going to interpret it in a different way. Now we'll think of these different valuations as ways the worlds could be as far as we know, given the information we have. So instead of thinking of the world as all of these valuations together at the same time and undecided in between them, the world is just one of them. But we don't know which one it is. So the world, in this case, goes beyond what we know of it. And in fact, it goes beyond what we can know of it. The valuations model our knowledge and ignorance by showing the different places the borderline could be given all of the information that we have. So on this picture, statements are either knowable, if they're always true in all of these different ways things could go as far as our knowledge can see, or refutable, they're always false in all of these ways that the world could go, or they're undecidable, if our possible knowledge doesn't contain the information required to decide the matter. This is a classical two-valued picture, and even more than the supervaluationist, because tautologies are true in every valuation, so they count as not only true but knowably true, and the world just is a two-valued row of a truth table in the traditional way. And this is what's called epistemicism. the idea that vagueness is a matter of knowledge. So let's look at what epistemicism has to say about the Sorites paradox. Now, the world will supply a borderline between the red and the not red. So, the numbers look exactly the same as we did before. Maybe I is the place where we have the transition, or maybe J is the place where we have the transition between truth and falsity, or maybe it's somewhere else. There's a range of different possible valuations, and now instead of thinking the world as being undecided between those, the world just is one of those, but we don't know where it is. It could be that this is the cutoff point between red and not red, or this is the cutoff point, or anywhere in between, or anywhere in a reasonably large range. Our information that we have isn't enough to decide. This is what epistemicism says about the Sorites paradox. The premises aren't all true, and one of the premises is false. It's just that we don't know which. This is a beautiful picture and a way to keep our two-valued interpretation, despite there being a great deal of vagueness in the world. Assigning a value 1 doesn't mean that the statement is determinate, or precisely true, or fixed. It just means that it's true. And perhaps things will be true, despite our inability to show that they're true. This is a sensible picture of the world. However, it too has some surprising consequences. On this view, like with supervaluations, there is a point along the strip which is red and where its immediate neighbour isn't red, despite their being indistinguishable to the naked eye. Now, redness, despite being defined in terms of what we can see, on this view outstrips what we can see. This leads to a really important question. How is that borderline drawn if it's not decided by us? Isn't the concept red our concept? How is it going around cutting boundaries beyond our capacity to detect them? Now, some people have gone so far as to ask whether the resulting view of the world, in which all concepts draw two-valued boundaries beyond our capacities to recognize them, aren't really modelling vagueness anymore and are just modelling our own ignorance. So there you have it. That's a whirlwind introduction to different approaches to vagueness. We've looked at the Sorites paradox as our focus, and we've used that as a prompt to ask questions about the assumptions we've made in our two-valued formulation of logic. We've then tried to give a few different answers to those questions. In the previous lesson, we looked at many-valued logics, which revise those two-valued assumptions. And in this lesson, I've looked at classical two-valued approaches to vagueness that attempt to clarify the assumptions we need to make in the two-valued approach. These are all issues in the philosophy of logic. And we've reached a point where I'm not going to tell you the right answer to these questions. Not because I don't think there's a right answer, but because all of the options we've looked at are in active research right now. The philosophy of logic is the task of reasoned reflection on how the tools of logic are interpreted and applied. And you don't expect advances to come in this interpretive endeavour by throwing out all approaches other than one. Each of these perspectives provide useful insights, and those of us that actively work in the philosophy of logic are still coming to grips with how to understand these tools. Some philosophers of logic are motivated about questions about logic that come from different areas of philosophy, like questions in metaphysics, questions about what exists, what's real, what's fundamental, or questions in epistemology, questions about what we can know and what's reasonable, or questions in the philosophy of language, like how truth and representation works, or what meaning is and how we can learn it. Each of these domains of philosophy come with their own questions and traditions, and each of them connect up with logic in different ways. And some philosophers of logic are motivated by questions about logic that come from inside of logic itself. And here there are two broad traditions, whether you start with models and interpretations, or you start with proofs and rules. Which of these things should come first in our explanations of logical concepts? The relationship between models, like valuations, or proofs, like proof trees, and how logic is to be understood and applied is an active area of research in the philosophy of logic to this day. So we've come to the end of this little introduction to logic and philosophy. I hope you've enjoyed it.